Okay guys, so next we will continue with the case number 3. So in this case number 3, when you have the complex pole, okay, so for example here in the slide, if you can see, you have the fs equaling to 4s plus the value of x divided by s squared plus 2s plus 5. So obviously these fs functions here is the proper functions, therefore you can factor it out into different terms adding up together. But like you can see here, you cannot be able to stipulate that into different root multiplied together. Why is that? Because if you try to do that here, you will see that we have the two complex root. Okay, so in this case you can double check that by using the minus b plus minus square root b square minus 4ac divided by 2a. So in this case, if you want to find for the roots of the s squared plus 2s plus 5 here, so in this case you will have the value of a which is equal to 1, b equal to 2, and c is equal to 5. Therefore you plug it in, so you will have minus 2 plus minus square root of 2 square minus 4 multiplied with 1 multiplied with 5 divided by 2 multiplied with 1, and that's become 2. So here you will have minus 2 plus minus. So inside the square root sign here you will have 4 minus with the 20 and then divided by 2. So that would be minus 2 plus minus with the square root of the minus 16 and divide by 2. So if you continue finding here, you will have square root 4 multiplied with the square root 4 and multiply with the square root of 1. And remember, square root of 1 is equivalent to the value of I, and then you divide that by 2. So here you have the minus 2 divided by 2 plus minus square root 4 here, that's become the value of 2. So you have 2 multiplied with square root 4 i's, and that divided by 2. So the first terms in front or the side here, you will have the minus 1 plus minus with the square root of 4i, and here again the square root sign here, that's become 2i's. Therefore your therefore you will have two different roots. So R1 here is equivalent to minus 1 minus with 2i's, and the R2 here is equivalent to minus 1 and then adding up with the value of 2i's. Okay, so you have the complex roots, therefore you can make that to be equivalent to so again here the maximum degree here is 2, means you need two variable or two constants. So you will have, let's say the first one is the a, and then adding up with the b. So a here will be s minus with that minus 1 minus 2i's, and the b is equivalent to s minus with minus 1 plus with the 2i. Therefore your fs here will be a divided by s plus 1, and then you have plus with 2i's, and adding up with b divided by s minus becomes plus 1, and then minus plus become minus 2i. Okay, so as you can see here, so we stuck with the we are stuck with the complex pole, that is the value of I, and that is I. So if you continue finding the value of fs here, so you will have 4s plus x divided by let's say s plus 1 s plus 1 plus with 2i's, and multiply with s plus 1 minus with 2i's equaling to a divided by s plus 1 plus 2i, and then that you need to multiply with s plus 1 plus with 2i multiply with s plus 1 minus with 2i, and again adding up with b divided by s plus 1 minus 2i, multiply that with the s plus 1 plus 2i, and multiply that with the s plus 1 minus with 2i. So that 2i cancel out, that's minus 2i, that's minus 2i, cancel out. And here again, this one and this one, we need to multiply with that term. So you will have 4s plus x, and that's become a multiplied with s plus 1 minus 2i left here. And then adding up with b multiplied with s plus 1 plus 2i. Again, in this case, you can see that when we cross multiply a and b here, we will start with the value of minus 2ai, and that is plus with the 2bi. So that cannot be eliminated out. Therefore, when you have the complex pole, we will not try to use the normal step as we did in the previous two cases. However, an alternative way for that case is that when we have the complex pole, we will try to map the root of the complex pole with that of the multiplications between the sines and the exponential terms, or the cosine with the exponential terms. So we will try to express that given expressions at, let's say, bs plus c. So b stands for 4 and c stands for the value of x, and divided by, let's say, s plus a squared plus w squared. So we will try to express the given expression here in terms of this case, the frequency functions for the multiplications between the exponential and the cosine terms. So let's say this: when we have 2 squared plus s squared plus 2s plus 5, and makes that become 2 squared plus 2s, and then plus 5 here become plus 1 plus with 4. So we want to transform this one into the form that is equivalent to that one. So you will need an additional of two difference constant. One is 1 and another one is 4. So this becomes the value of s plus 1 squared, and the value of 4 that become 2 raised to the power of 2. Therefore, the angular frequency W here is equivalent to the value of the 2. So we are done with the denominator part. Therefore, our 4s plus x divided by s plus 1 square plus with the 2 square. That's perfect. And next step. So when we have the denominator similar to these functions, so we will look back into the the Laplace transform table, and then we map with the terms or the functions that consist of denominator similar to this case. So we know that the exponential of the at multiplied with the cosine angular frequency t, that's equivalent to s minus a divided by s minus a squared plus with the angular frequency square, or the exponential of the at sine wt is equivalent to w divided by the s minus a squared plus that of the w squared. So we will focus on using these two properties here. Alright, so then for the denominator part, we will have 4s plus 4, and that's adding up with 4, right? So from x here, we separate that into 1 4 and another 4. So you divide that by the denominator, that remains the same. All right, and then we will try to factor out the value of 4 here. Okay, so you will have 4, and that become s plus 1, and that become the additions of the 4 and the whole of that divided by s plus 1 square plus the value of 2 square. Okay, so now we have two different terms adding up together. So the first one here, right? So the first term that you have is that the terms of this one, And the second one, or the second term here, we have the term for the 4. So you can see that we require these functions and also these functions as well. So let's have a look what it will be like. Therefore that will be 4 and then multiply with the s plus 1 and that divided by the s plus 1 square plus the value of 2 square. Okay, and then plus with 4 divided by s plus 1 square plus with the value of the 2 square. So the first term here, you can see that it's quite similar to the multiplication between the exponential terms and the cosine terms, whereas the second one here is similar to that of the exponential in combination with the sine terms. Okay, but in the second case here, you can see that this one we have the bill and this one we have the bill. Therefore, we have to make that into W. So in this case, our W here, the angular frequency here is equivalent to the value of 2. Therefore, in this case, you need to transform the value of 4, or you need to change the value of 4 here into the value of 2. Okay, let me write that down. So you will have the value of 2 and that multiplied with the value of 2 divided by s plus 1 square plus 2 square. So as you can see, we have that the bill, we have that the bill, that is the bill, but that is the w square. So that is s minus a, that is s plus a. So our a here in this case is minus 1. So never mind, we will do that again. And then for the first term here, number 4 here can remain the same. So you have s plus 1 divided by s plus 1 square plus the value of 2 square. So that is mapped with that case. Alright. Therefore, this is our fs. So we rearrange from the complex pole into the exponential multiplications of the exponential with the sines and with the cosine, and here is what we have got, right? And then our next step, after we know everything, we have to find its inverse Laplace transform in terms of the t, in terms of the time domain. So here again, the value of 4 at the constant, you can just write the constant here at the front. And then let's consider on the first term first. So we forgot the addition sign here. So that's similar to the exponential multiplication with the cosine terms, but the value of a here is plus, but that's become minus. So in our case, we got the addition sign, therefore our exponential will be raised to the power of minus 1t. Alright, then we have the cosine of the WT left. So cosine of the WT, our WT in this case is the value of 2. So therefore, we will have the cosine multiplications of 2t. Right, we are done with the first terms, and then additions with the second term. So this number 2 here remain the same. So in this case, we have already expressed the last term to be in compare with the exponential multiplied with the sine term. So then next we can have the multiplications of the value constant 2 with the exponential of minus 1t, and then we have the sine of WT left. So sine of W here. So the bill or the angular here is the bill. In our case is the value of 2t. So that is the final result for the inverse transforms of the complex pole when you have the complex pole. So you need to express that in terms of the multiplications between the exponential and the trigonometric functions first, and that is how we derive the transform. Okay, so let's say what's next we have to do. Sorry. Okay, right? After we're done with the complex pole, let's jump into these ones. So as you can see from the slides, let me remind you again of the improper and the proper functions. So in the GS function here, you can see that we can stipulate that into the multiplication between the s plus 3 and the s plus 4, and that is the case number 1, which is the distinct pole. Then you can further continue with the inverse Laplace transform method. But the HS function here, you can see that this is the improper functions because the degree of the numerator and the denominator are the same, and that is the improper function. So we cannot apply the technique that we discussed earlier. We need to make that fs functions to be the proper function first. And how about the last one, the fs? So the fs function, even though you have the proper functions, but you can see that that proper functions is multiplied with the exponential function. This is not the rational function, therefore we cannot apply the technique that we discussed earlier. So next, if we have the improper functions, right, what would we do? Okay, like in this case, okay, right. Okay, so next, suppose that you have the improper functions. Okay,